I have here a ramp on which I have my bone-crushingly strong magnets and two aluminum rails, which are together connected to an oscilloscope. When I put a metal rod across the two rails, I've effectively created a loop of wire, which has magnetic flux in it. There are two observable phenomena we're about to see as a result of Faraday's and Lenz's law. As the rod rolls in between the magnets, the magnetic flux of the wire loop is going to change. Faraday's law says this will create a voltage, which we'll be able to read on the oscilloscope. Coupled with Lenz's law, this voltage is going to create a current that's going to oppose that change in magnetic flux. What that means is the metal rod will slow down once it enters the magnetic field. I'll start with a non-magnetic steel rod. We see a very clear peak in the voltage, but not a very obvious slowdown. What if instead I use aluminum? Aluminum's so light and conductive, it actually comes to basically a complete stop and can't even overcome the friction to restart its rolling. We can angle up the ramp to increase the force of gravity and maybe get it to finish rolling down. You'll notice the induced voltage is much weaker with the aluminum because it's moving so slowly, the flux can't change very quickly. Here I added a handle to the aluminum, so I can push it back and forth through the magnetic field, and we'll see how that affects it. And now we can get voltages on par with steel because I can change the magnetic flux faster. In this case, the difference in conductivity between aluminum and steel doesn't affect the voltage I get, because the changing magnetic flux is what induces the voltage, and that doesn't have to do with the conductivity of either metal.